Hello, my Algebra 2 students. We are starting a new unit. Unit 9 is all about rational functions, which is basically a fancy way of saying fractional expressions or fractional equations. So you always have that fun little picture on the first page, and we'll actually talk about what that is momentarily. For the whole unit, it is not an extended unit here. We kind of get through the basics. We do have a quiz, and then a couple more days after that. So let's hop right on in to day 1 here. And it's saying rational functions have the form of f of x equals p of x divided by q of x, where p of x and q of x are both polynomials. So that's what I meant about the fraction thing. So it can be as simple as f of x equals like 1 over x. That would be a nice simple one to look at. Or you could have larger polynomials where maybe, you have a binomial in a piece of it, or you could even have trinomials and so on. So there's all sorts of different examples. So like, 4x squared plus 2x plus 11, and then all over 7x squared minus 9, whatever. So you can have any type of polynomial in the top and the bottom, as long as, of course, the denominator isn't, 0. As for what they look like when you graph them, well, depending on how complicated they are, the graphs can definitely change. But all the graphs, if there's an x in the denominator, have an asymptote. All right, so an asymptote, asymptote, all right, is a line that a graph approaches as you get further away from 0. So the graph gets like really close to it, but it never crosses it. That's the idea with it. So if we look at a really simple example, like y equals 1 over x, and I'll grab my calculator here. If I put into y1 just 1 over x, so you can see what this looks like, I'm just going to zoom 6. This quirky little graph has an asymptote right there at x equals 0, right? Because it kind of disappears at that point because it can't be equal to 0, or otherwise it would end up undefined. We'll get to that in a moment. So it kind of looks like this, and you're going to put a vertical dotted line there to represent that asymptote, and then looks kind of like that. This thing is called a hyperbola. We are not going to focus a ton on the graphing, but the graphing does help us understand where values of x can happen and where they can't. Another example of one that's slightly more complicated is if I have y equals, x and then over x squared minus 4. So same thing, just to kind of give you an example of like what this could look like. I'm going to use the alpha y equals here. So if I go x and then over x squared minus 4, and then hit graph, you can have more than one asymptote. And so this funky little graph here actually has asymptotes back here at -2 and at +2. So if you draw in those little dotted lines and then kind of draw the general shape of this graph here, you can at least follow that, like, oh yeah, I can see the graph like disappearing in those lines, being kind of little barriers of what's going on. Next year in Math 12 and in pre-calc, you'll do a lot more investigation into how those graphs look the way they do. For now, what we're going to focus on is more the algebraic end of things and being able to simplify and so on. All right. The little details of the graphs that we will cover, though, is being able to find just an x and a y-intercept, because that's something that we've done with every single function that we've covered. So y-intercept, you got to remember, that's when x is equal to 0. X-intercept is when we set y equal to 0. So let's do it. Over here, if we plug in 0 for x, we'd get 0 plus 6, 0 minus y, or 0 minus, 3, and then 6 over -3, that would give us -2. So the y-intercept would be the point 0, -2 for this particular function. And then if we want the x-intercept, we'd set y equal to 0. So if we put 0 on the left side and make it x plus 6 over x minus 3, I tend to think of this as putting that over 1 and cross multiply. I think a lot of times you guys just think of, hey, I'll multiply x minus 3 from both sides to get it out of that denominator, which that gives me 0. And I'm just left with 0 equals x plus 6. And then subtract. The x-intercept here would end up at negative 6, 0. And keep in mind, you can have more than one x-intercept. You cannot have more than one y-intercept. Right? So when it says for which values of x is the function undefined, all right, well, when we think undefined, what we should be thinking about, is when the denominator is equal to 0. If I try to divide by 0, it does not make sense, all right? That's what's going on. So if we take that denominator of x minus 3 and set it equal to 0, we'd come out with x equals 3. That's the value that would make it undefined. Because if we said, all right, well, let's calculate f of 3, and we put a 3 into the top and a 3 into the bottom, we'd get 9 over 0, and that's garbage. That doesn't make any sense, all right? And so what that means is that this would be undefined at x equals 3. It also means that's when the vertical asymptote would happen. So anytime the function is undefined, that is where it produces a vertical asymptote because the graph literally can't exist there. And so you get those little lines where it can't cross and where it doesn't exist. All right, for this one, state the domain in set builder notation. We usually called it just set notation, but you guys are familiar with set notation. That's the fun, fancy curly bracket where we go x such that. All right, well, let's think about it. There are no other issues other than where it's undefined. So it can be everything but 3. So if it can't be 3, then what we can say, if we think about this like on a number line, is it would be an open circle at 3, but it can be everything to the left. It can be everything to the right. So it can be less than 3, or it can be everything greater than 3. And that would be our domain in set notation. In interval notation, we go from negative infinity up to 3, but not including it. So a parenthesis, union with 3, and then on up to infinity. So that's our way of saying that we're leaving out that value of 3 there. The other way to do that set notation, that's a slightly like shorter hand, is you can say x such that x is just not equal to 3. That would be acceptable as well. That's a little easier to deal with than this. So you might want to make yourself that note that you can do either one. On to the next page. Here comes the algebra that I was talking about. So here it says, it even reiterates you're going to do more with those graphs in pre-calc. That was just a little intro. So now let's focus on the fact that given a function, can we find all the values of x for where it's going to be undefined? So we said that that's when the denominator is equal to 0, and then state the domain. All right, so let's try it. So if we do this first one, I don't care what's happening in the numerator. Focus on the denominator only. So if we take 2x squared plus 11x minus 6 and set it equal to 0, the idea is then we want to solve for x. So a quadratic function, the hope is that it factors. If it doesn't factor, quadratic formula would be my suggestion, but completing the square also works, right? So I'd probably look at it in that order. So with this one, your option for factoring is you'd want to try a little slip and slide. So if we multiply this over, we would get x squared plus 11x minus 12. And then we'd be looking for what adds to 11, multiplies to give you 12. All right, well, this one's going to work. So 12, if we go 12 and 1 and make this a positive 12, negative 1, that'll work with my signs. Remember to finish the slip and slide process. So this is already simplified, so slide the 2 in front. This we can simplify. And then let's just double check. So this would be 2x squared. Outsides would be 12x. Insides minus 1, so that works with the 11. And then last would give me negative 6. Perfect. All right. So if we keep on going, set each factor equal to 0 and solve. So this would produce -6. This one will give me positive 1/2. And so when it says find the x values for which the function is undefined, this is it. Those are the x values right there. If you want, you could write it in some nice like curly brackets like this or something. Oops. And that would be fine too. Otherwise, that's as far as you need to go. All right. And then for part 2, so that was part I, here's II, state the domain. All right, well, the idea is once you figure out where the function's undefined, you have to take those values out of the domain. All right, so remove these values from the domain. I always think it's best to give yourself a number line. So -6 is smaller than 1/2. Open circle, we're not going to include those. So it could be anything to the left, anything in the middle, anything to the right. This makes it really nice. Let's say if we were to answer it in interval notation, because now we can read it from left to right. Remember, even though you don't mark it, negative infinity is all the way to the left there, up to -6. Close it up with a parenthesis, union, -6 to 1/2. Close it up, union with everything over here from 1/2 up to infinity. If we were to use set notation, here's where I would suggest x such that x just can't be equal to -6 1/2. All right. So a couple different ways. It didn't specify, so I figured I'd just mention both. All right. Save part B. We'll recap with that guy in class. That's a good one to look at. All right, if we slide on down, when it says, for example, 3, which of the following represents the domain here? Well, then at this point, hopefully we know what to do. Ignore the numerator, take the denominator, get going. So set this guy equal to 0, factor, and solve for x. So this is going to be your video question right here. I want to know what answer did you come out with? And of course, we'll talk about it in class as well. All right, moving on to that next page here. We've got some review topics that come up in these first couple days. The first one, given two functions, you were asked to do f of g of -2 and then f of g of x. That is called the composition of functions. And we did this back in our functions unit, which I think was unit 1. Composition of functions means you always start on the inside and you work your way out. So starting on the inside here, we would look at g of -2. So I'm going to write that we do that first, which means we're just going to plug -2 into that g function. And so this gives us -6 minus 1, or -7. And then we take the original and we plug in place of g of -2 the answer it came out to give us. So we essentially take that answer and then keep running with it. So now over into the f function, we can plug in 2 times -7 plus 1, and then all over -7 plus 5. Right? That'll give us -14 plus 1, which is -13. -7 plus 5 is -2. And so we can leave this one as 13/2 or 6.5. Either one is perfectly fine because they're both exact. All right. So when you're given a number, we plug in, we get an answer, we follow that number all the way to the end, and that is the final answer there. In terms of this next one, if we are left with x here, then the final answer is going to have x in it. So this notation, even though it looks like fog, remember, this reads as f of g of x. So we start on the inside first. So g of x simply is the function 3x minus 1. Now we take that and we plug it in to the f function. So we're going to take this entire thing and plug it in. All right. What that means for us is over into the f function, wherever we had an x. So here and here, we are now putting 3x minus 1 in those spots. So that means that it's 2 times whatever you plug in plus 1, and then over whatever you plug in plus 5. Well, what I'm plugging in here is the 3x minus 1 there and the 3x minus 1 here. So hopefully as you see this, it's coming back to you. All we're going to do is clean up. Let's distribute. We get 6x minus 2 and then plus 1. And then 3x minus 1 plus 5. I can just drop those parentheses. So this will give me 6x minus 1 on the bottom, 3x plus 4. If I can simplify it, great. If not, no worries. And if you're saying, how do I know if I can simplify? That's what the next couple days of this unit are going to be about. So for right now, this can't be simplified any further. This is actually just what f of g of x is equal to. So we created a new function that did what the old two did in 2 steps. This one would now just do it in 1. All right. The next thing, inverse. This is also review. Oh my goodness. So inverse of a function means that you switch the x and y values, and then you're going to solve for y. So we did this a couple times earlier in the year. So let's get going. The difference here is there's 2 x values, 1 y. You're still going to swap both. So when we go to switch, x will go on the left, y goes in the numerator, and then y goes again in the denominator. So it's y minus 2. From here, you can multiply this y minus 2 over, or you can think of it as throwing it over 1 and cross multiplying, whichever way seems to make the most sense to you. All right, when we do that, I'm going to end up with x times y minus 2, and then plain old y over here. What I want you to do, distribute that x. So we get x times y minus 2x and then equals y. So now if our goal, we switch the x and y, if we want to solve this for y, we need to get our y's together so that we can solve for just a single y. And now I know that sounds a little weird, but if we move this on over, so subtract xy, subtract xy. All right, I'm going to be left with a minus 2x over here, and then y minus xy. To get a single y here, I can actually factor out the y as a GCF. And so to do that, divide y out. So you can kind of think of as divided by y here, which would leave me with 1. Divide by y here, I'm left with minus x. And now last little step. Divide by 1 minus x to get the y all by itself. Right? And so what you're left with is negative 2x, and then over the quantity, 1 minus x. This is the inverse of the original function. And so just a little note to self, remind yourself that you need to get both y terms on one side, and then we can factor the y out. We'll save this second one to do together in class, because sometimes it can be a little tricky, so it'll be nice that we can chat about it. And then that very last question we will save for class as well. All right, thanks so much, guys, for watching.